Hi all, welcome to another lecture on business statistics. Last week Dr. Wong covered chapter 12, which was Introduction to Simple Linear Regression. This week I will continue with chapter 13, which is Introduction to Multiple Regression. So what are the objectives for this chapter? In this chapter you will learn how to develop a multiple regression model, how to interpret regression coefficients, how to determine which independent variables to include in a model, how to determine which independent variables are most important in predicting a dependent variable, how to use categorical independent variables in a regression model. So this lecture will be divided into two parts. The first part will be looking at the basic interpretation, and the second part will cover the assumptions involved in analyzing multiple regression. So what is multiple regression model? This is how you can present a multiple regression model. This is an extension of your simple linear regression. In simple linear regression, you have one dependent variable and one independent variable. Whereas in multiple regression, you must have one independent variable, one dependent variable, and multiple independent variables. Okay, at least two or more independent variables, then only we call them multiple regression. So the basic equation will be written like this. Y1 is your dependent variable. So beta 0 is your intercept. Beta 1 is the slope for independent variable 1. Beta 2 is the slope for independent variable number 2. And beta k is the slope for independent variable k. And epsilon is your error, the error term, okay, which is the random error. So here we have the equation written in a simpler format. yi equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus error. So y is your intercept. Beta 1 is the slope of y with variable x1 holding x2 constant. Beta 2 is the slope for y with variable x2 holding x1 constant. And this is the error term for the random error in y for observation I. So for multiple regression testing, we can use several software. Some of them are like Excel, JMP, and Minitab. But in this class, we will use SPSS. So I will show you the result from SPSS. So when we do multiple regression equation, we have two variables here: independent variable 1 and independent variable 2. So what we are going to look at is we want to see the slope of x1 and the slope of x2. So once we get the slope of x1 and x2, then only we can write an equation: y equals to beta 0 plus beta 1 x1 plus beta 2 x2. So we will look at an example with two independent variables. Here is where a distributor of frozen dessert pies wants to evaluate factors thought to influence demand. So the dependent variable is pie sales. The independent variables are price and advertising. Data are collected for 15 weeks. So the data is presented this way. Column 1 represents your week number 1 to week 15. Column 2 represents the pie sales, which is 350 for week 1, 460 for week 2, and so on. And then column 3 is price for each week. What is the price set for the pie? And column 3 is your advertising, which is in hundreds. So if you put the number here 3.3, it means you spend $330. Okay, so the multiple regression equation will be sales equals to beta 0 plus beta 1 times price and plus beta 2 times advertising. That's a model we want to develop. How do we set up the analysis? This is SPSS. Since you have already installed SPSS, you will click Analyze regression and linear regression. Okay, analyze regression and linear regression. Then we will go to the next page where you get a dialog box like this. You will put the dependent variable from here to here. The two independent variables will go here. So this is the basic setup for multiple regression analysis. For simple linear regression analysis, you have one dependent variable and only one independent variable. So this is the basic setup. Okay, and then what you need to do is you have to set up two more buttons here called statistics and plots. Okay, when you click the button statistics, you will get this. Okay, these are some of the assumptions you need to test for multiple regression. So the basic output that will be given in the statistics component is this is the default estimates and model fit. The rest of the output is not given, so you have to actually additionally click these boxes so that you get additional output to test the assumptions. So, and then we click the button plot and you get another dialog box. You have to click histogram, normal probability plot, and produce all partial plots, and also additionally ask for this additional plot which will be used for testing an assumption called constant variance. Once you run the model, you'll get a long list of output. Okay, to write an equation, we will need this table called coefficient table. They will have column number 1 here, which gives you the unstandardized beta coefficients. Okay, so to write an equation, you begin with the constant. This is your beta 1, this is your beta 2, this is x1, this is x2. So the constant value will go here, the price will go here, the advertisement beta will go here, x1 is here, x2 is here. So that's how you will write an equation. So we have a beta value here. What is the difference? Here the beta values are in the original unit of measurement of the independent variables. Like here we have sales. Sales was measured in hundreds. Okay, so whereas here they will remove all the unit of measurement. We can compare across. What the standardized coefficient tell you is out of these two variables, which has a more significant or more stronger effect on the dependent variable. And the conclusion is advertising has a more stronger effect on the pie sales. Okay, pie sales. So this is how we will write an equation. Sales equals to 306.526 minus 24.975 times price plus 74.131 times advertising. So what does the beta value here means is when price increases by $1, okay, sales will decrease by 24.975. Okay, $24.975. Okay, here when advertising increases 1 unit, that means $100. Huh? Okay, when advertising increases $100, sales will increase by $74.131. Okay, and that's how the beta value is interpreted. And negative means the relationship between price and sales is the inverse. Positive means they move in the same direction. Okay, that's how you interpret the beta values. Okay, what is the purpose of doing this regression equation is we have already covered 15 weeks. We collected data for 15 weeks. We now want to predict the sales value for week 16. Okay, so what we will do is we will plug in the price that is expected for week 16 and the advertising for week 16. Write the equation, and in the bracket we will plug in the numbers. Okay, again here advertising is in hundreds, so if the advertising is 350, you cannot put a 350 in the bracket. You have to put a 3.5. Okay, 3.5, because 3.5 times 100 is 350. So once we plug in the numbers, we will get a predicted sales of $428.62. Okay, $428.62. This is what we call as prediction of a future value given the values of the independent variables. So when we do multiple regression, we also have a coefficient called coefficient of multiple determination, which is the R square. Okay, what the R square reports is the proportion of total variation in Y explained by all independent variables taken together. So how do you calculate the R square? R square is a sum of squared regression divided by sum of squared total. Okay, here regression sum of squares divided by total sum of squares. Okay, so when you get your regression output, you will get an R square in the first box called model summary. In model summary, we have a 0.521, which is the R square. How do you get the R square? Okay, here we have a regression sum of squares 29460. We have a sum of squares total 56493. So we take this regression sum of squares divided by total sum of squares. We will get this number 0.521. Okay, the R square ranges from 0 to 1, maximum is 1. So we will convert this into percentage times 100. So we will get 52.1% of the variance in pie sales can be explained by the two independent variables, price and advertisement. Okay, we have another 48% unexplained variance. That is because we have not included other predictors or independent variables. Okay, predictors or independent variables. So how did they calculate this F square is we will take sum of squares divided by degrees of freedom. We will get mean sum of squares. We will take residual divided by the degrees of freedom. We will get mean square residual. So mean square regression divided by mean square residual, you get F value, and then we will look at the table value to compare whether it's significant or not. So here we will also look at the p values. This is what we call as the p values. We have another value called adjusted R square. Okay, when you include more independent variables, R square never decreases. Okay, this can be a disadvantage when we compare models. So if you want to compare two different models, one with 5 independent variables, another one with 10 independent variables, the model with the 10 independent variables will have a higher R square. The one with the 5 independent variable will have a lower R square. So to penalize for this complexity, we will do some adjustment to the degrees of freedom. So how do we calculate this adjusted R square is, here adjusted R square equals to 1 minus R square times n minus 1 divided by n minus k minus 1. So the adjusted R square shows the proportion of variation in Y explained by all independent variables, adjusted for the number of independent variables used and also sample sizes. Okay, two things, number of independent variables and sample sizes. So it penalizes excessive use of unimportant independent variables. It will be smaller than R square, and it is only useful for comparing different models. Before we assess all other values, the most important table that we will look at is the table called ANOVA. Okay, in the ANOVA table, they will give you an F test. Okay, the F test is to test whether the overall model is significant. Okay, so this F test shows if there is a linear relationship between all the independent variables considered together and the dependent variable, which is your Y. So how do you write the hypothesis for F test? H null equals to beta 1 equals to beta 2 equals to beta 3, beta 4 until beta k equals to 0. What it tells you is there's no linear relationship between your independent variable and the dependent variable. The alternative, which is H1, will tell you at least one of the betas are not equal to 0. What it tells you is at least one independent variable has some effect on y. Okay, some effect on y. So how the f-test is calculated? Okay, f-stat equals to MSR divided by MSE. What is MSR? Mean sum of squared regression. MSE is mean sum of squared errors. So the MSR is calculated by SSR divided by K and SSE divided by N minus K minus 1. Okay, N minus K minus 1. Okay. So when we look at the table in F, for F, it has 2 degrees of freedom, one for the numerator, the other is for the denominator. So the numerator degrees of freedom is equals to K, which is the number of predictors you have in a model or independent variables. The denominator is your sample size minus number of independent variables you have minus 1. Okay, minus 1. So this is how you can set up the f-test for the overall significance. So we have the hypothesis already written. Degrees of freedom 1 is K, which is equals to 2 independent variables. Degrees of freedom 2 is equals to 12 because N minus K minus 1. N is 15, K is 2 minus 1. So 15 minus 2 minus 1, you get 12. So if you look at the F table, you get a critical value at 5%, alpha 0.05, denoted as 3.885. So if you get an F-stat which is lower than 3.885, do not reject H null. If you get an F-stat which is greater than 3.885, you will reject the H null. So that's the decision given here. Okay, again, if the F-stat is less than 3.885, do not reject the H null. If the F-stat is greater than 3.885, reject the H null. Okay, since F-stat statistic is in the region of p-value less than 0.05, reject H null. Okay, reject H null because 6.5386 is actually in this region, right? Okay, so the conclusion is there is evidence that at least one independent variable affects y. The same test can also be done by looking at the p-value. Since our alpha value is 5%, so this is the column that gives you the p-value, which is a significance, 0.012. So the p-value 0.012 is less than alpha 0.05. So the null hypothesis is rejected, and we will conclude the overall model is significant. So when we do multiple regression, this is the plane that is used to estimate the multiple regression. This is your y, this is your x1, this is your x2. Okay, so we have 2 independent variables predicting the y. So what we will do is we will have a slope for x1, we will have a slope for x2, okay, and we will develop this equation. Beta 0 equals to beta 0 plus beta 1 x1 plus beta 2 x2 equals to y, and we will substitute the x1 and x2 into the equation. We will get what we call as the y hat. Okay, y hat or estimated y. So when we take the actual y minus the estimated y, we will have a difference here. Okay, the difference. Okay. Sometimes your actual y will be smaller than the estimated y. In some situation, the actual y can be the same as your estimated y. Sometimes your actual y can be higher than the estimated y. So you can have the residual as negative, 0, or positive. So the equation that we want to develop here is the best fit equation is found by minimizing the sum of squared errors. So you square all these errors, and which line minimizes this error will be the best regression equation that we find. Okay, that's how we will interpret the model. So we will stop here for the first part. We will continue with the second part. Thank you.